In the last lecture, we proved that a Banach space is a Hilbert space if and only if it holds the parallelogram law. So this is very important type, and also there are some question related to that theorem. So question number 1. So what is the statement? Show that, this is very important question, show that the parallelogram law is not true, show that the law is not true in LP space where P is not equal to 2. So that is given condition that P is not equal to 2. Now we are talking about the LP space. So first, what is LP space? So just I revise it. So what is LP space? Which consisting a n tuple element and so on up to xn, such that xi belongs to R or C. So this is R. Basically it belongs to field. So I take it is from R. Now, and this is just right, it is from field. So norm of x P in this case is absolute value xi raised to power p, I is running from 1 to n, and then the entire sum raised to power 1 by p. So that is a norm defined in the LPC. So remember the definition of LP space, and it is a norm-linear space. Also, it is a Banach space. It is a norm-linear space. Now, I take this 2 vector from this x is equal to 1, 1, 0, 0, and so on up to 0, 1 vector, and second vector y, which is a 1, minus 1, 0, 0, and last term is 0. So this is a 2 vector xy. It belongs to, because entries are real number, so it implies x comma y belongs to LP space, right? So we can also use in this case this field is basically R. So here set of real number, and we can use this as set of real numbers. Now xy belongs to LP space. So what is sum x plus y? If I am taking the sum of 2 vector, so this is 2, 0, 0, and 0. Similarly, if I am taking the difference of 2 vector, so 0, 2, 0, 0, 0, right? Now I define the norm linear, I define the norm of these vectors. So first this is a x plus y and this values. Now I define the norm of these vectors. So first I am taking the norm of x. So what is norm of x with respect to p? So this is a bracket 1 raised to power p plus 1 raised to power p plus so on 0, 0, 0 and raised to power 1 by p. So this will be 2 raised to power 1 by p. Similarly, norm of y p, so this is equal to, again on same line, so again it is 2 raised to power 1 by p. Now what is norm of x plus y p? This is, so this is a 2 raised to power p plus 0, 0, 0 plus 0, then raised to power 1 by p. So this is a 2. Similarly, norm of x minus y p, which is again equal to 2 on same line of action. So what is parallelogram law? So just understand. So parallelogram law is norm x plus y p raised to power 2, norm x minus y p raised to power 2, and this is norm 2 times norm xp raised to power 2, 2 times norm of y raised to power p raised to power 2. So this is the left hand side and this is the right hand side. So what is, we check that left hand side. So left hand side, so what is the value of this norm of x plus y p, which is equal to 2. So this is a 2, this value is 2. If this value is 2, so this value is 2 raised to power 2 plus 2 raised to power 2. If this value is 2, then it means 2 raised to power 2, 2 raised to power 2. This is this side, left hand side. So this is a left hand side and it is a right hand side. So what is right hand side? So this is 2. What is norm of x? So which is a 2 raised to power 2 by p plus 2 is common, 2 raised to power 2 by p, right? Because its value is 2 raised to power 1 by p, then taking square, so 2 raised to power 2 by p. Here again 2 raised to power 2 by p. So this can be written as 2 square into 2 raised to power. So this is a 2 raised to power 2 by p. So this values, right? So basically it is 2 raised to power 2 plus 2 by p, and this value is 2 raised to power 2 plus 1. So it means 2 raised to power 3. Now this term and this term, these are equal only when p equal to 2. Otherwise they are not equal. So in case of p not equal to 2, in case of if p is not equal to 2, it implies norm x plus y p raised to power 2 plus norm x minus y p raised to power 2. So this is not equal to 2 times norm x p raised to power 2, 2 times norm y p raised to power 2. So left hand side is not equal to right hand side. So it does not hold parallelogram law. So it means it does not hold parallelogram law. Hold parallelogram law. So it means it is a norm space and it is not a Hilbert space, because it is a Banach space, but it is not a Hilbert space because it does not hold a parallelogram law. So in our question, the statement was it does not hold a parallelogram law. Also, we can say that it is an example of Banach space which is not a Hilbert space. So this can be also written as give an example of Banach space. Give an example of Banach space which is not a Hilbert space. So this is very important question. So the examiner may ask in two ways. First, to show that it does not hold the parallelogram law, and second, give an example of Banach space which is not a Hilbert space. So in this way we can prove the given result. Now after that we are going to prove a very, very important result. So to go to that result, first of all, so just understand the definition of convex set. Convex set. So what is convex set? A subset E of a Hilbert space H is said to be convex, if it satisfies the given property. Which is that property? If we take two vector belongs to E, so it implies its linear combination lambda x plus 1 minus lambda y belongs to E. This is a xy vector belongs to E. So this linear combination belongs to this, where lambda lies between 0 and 1. So remember this. So this is a definition of convex set. Now basically it means convex set means, so if this is some space, and this is another space, so we have two space. Convex set means if we are taking 2 points, so one is this x and second is this y, and again here one is x, another is y. So linear combination mean lambda x plus 1 minus lambda y means it is a line, it is a point on the line, straight line which joining these point. So these point. If this line belongs to this set, means set E, then it is a convex set. But in this case, this line does not belongs to E. This line from this to this part is a part of E. This to this part is also part of E, but the entire straight line does not belongs to E. So it means it is not convex set. So what is this? This is an example of convex set. So this is an example of not convex set. So understand the definition with the help of geometrical interpretations. If we understand with the help of geometrical interpretation, then we can understand better. Now next theorem is, which is very important in the functional analysis, also in the Hilbert space. A closed closed convex subset C of a Hilbert space H, a closed convex subset of a Hilbert space H contains a unique vector of smallest norm So this is a definition of our question. So what is closed convex subset C of a Hilbert space, so which contain a unique vector of smallest norm. So this is very, very important result, so expected for examination. So to prove this result, now to understand it better, so just go through my notes, that is a book, Spectrum Functional Analysis. So you will find the entire theory of these theorems. Now proof of this result. So what is the proof? So to prove this result, first part, it contains a unique vector of smallest norm. So I define a d values, which is a smallest norm, means infimum of set of norm of X and X belongs to C. So what is C? C is the closed convex subset of Hilbert space H. So our bigger space, this is a H, which is a Hilbert space, and smaller space, so which is a C, which is a convex set. So this is a D, which is a given part. Now by definition of infimum, so by definition of infimum, there exists a sequence, say that is Xn in C such that there exists a sequence such that norm of Xn approaches to D as n approaches to infinity. So I take it as equation number 1, and this I can take it as, this can be taken as limit n approaches infinity xn, which is equal to d, so which is equation number 2. So which is equation number 2. Now xn and xm, these are part of C. And what is C? C is convex set. If C is convex set, then lambda xn plus 1 minus lambda xm belongs to C. So if I take lambda is equal to 1 by 2, so it means xn plus xm over 2 belongs to C. So which is equation number 3. Why? So here I take lambda equal to 1 by 2. So if lambda is 1 by 2, then 1 minus lambda is again 1 by 2. Now go to the definition of D. So by D, we know that what is D? D is the infimum. So D is always less than equal to norm of x for every x belongs to C. It means all the member of C satisfy this condition. So this is a member of C. So it means this satisfy the condition xn xm over 2. So this will be greater than equal to D. So which is a equation number 4. If I write it in the form of equation number 4, also it can be written as xn plus xm greater than equal to 2D. So this is equation number 4. So they are the same. Now in the Hilbert space, we know that parallelogram law holds. So by parallelogram law, parallelogram law. So by definition of parallelogram law, so what is the parallelogram law? Which is a norm of xn plus xm raised to power 2 plus norm of xn minus xm raised to power 2, which is equal to 2 times norm of xn raised to power 2 plus 2 times norm of xm raised to power 2, this value. So it implies left hand side, which is xn minus xm raised to power 2, this value is equal to 2 times norm of xn raised to power 2, 2 times norm of xm raised to power 2 and minus norm of xn plus xm raised to power 2. Now from this, if this is greater than equal to this, then its square is greater than equal to minus 4. If we multiply by minus, so this is less than equal to minus 4d square. So this is 2 times norm of xn whole square, 2 times norm of xm whole square and minus 4d square. So this is minus 4d square. Now equation number 2. This approaches to when m and n approaches to infinity. So this approaches to 2d square plus 2d square minus 4d square as m n approaches to infinity. So it implies norm of, so what is this, which is a 0. So norm of xn minus xm, it approaches to 0 as m n approaches to infinity. So it implies this sequence, xn sequence, is a Cauchy sequence in H, Cauchy sequence in C. Now what is C? C is the closed subspace of Hilbert space. So what is C? So since C is closed subspace of a Hilbert space. So what is Hilbert space? Hilbert space is complete. So closed subspace of complete metric space is again complete. So C act as Hilbert space. So C act as Hilbert space. If C act as a Hilbert space, just C act as a complete space. It means every Cauchy sequence in C are convergent. If convergent, so it means since C is complete, there exists X belongs to C such that Xn approaches to X as n approaches to infinity. So it implies, so since norm is a continuous, so norm of X can be written as norm of limit n approaches infinity xn. So since norm is continuous, so limit can be taken outside. This is norm of xn, so which is equal to d. So which prove our result. So x is a vector in C with the smallest norm. So what I get? I get x is vector in C with smallest norm, So after that we prove uniqueness. So if I take two vector of smallest norm, suppose that vector are x and x dash. So let x and x dash be two vectors in C such that norm of x which is equal to d and norm of x dash which is equal to d, such that it satisfies this condition. So what is my claim? My claim to prove in case of uniqueness x equal to x dash. Now again applying the parallelogram law. So what we get? We get norm of x minus x dash whole square. So which is equal to 2 times norm x square plus 2 times norm x dash square minus 2 times norm of x plus x dash whole square. Since on same line x and x dash belongs to C, C is convex set, so x plus x dash over 2 which belongs to C. By definition of D, this is x plus x dash over 2 greater than equal to D. Using this concept, so this is less than equal to 2D square plus 2D square, and here it is minus 4D square, so this is equal to 0. If this is equal to 0, then it means norm is less than equal to 0, but norm cannot be negative. So if norm cannot be negative, so it implies norm of x minus x dash equal to 0. If norm negative, then vector is again 0. If norm is 0, it implies x equal to x dash. So which prove the uniqueness. So which prove the uniqueness. So this is very important result.